Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and this is my fourth video in my new series on the Math Lovers book. In case you're just joining me, I have a 3-volume series which I call the Math Lovers book, which I completed in 2022, and you can buy this on Amazon if you want, Amazon.com. You can search for either the Math Lovers book or my name, David Tear. And like I said, there's 3 volumes. Each volume is $30 paperback, $9 Kindle. Anyway, you might want to check it out because I think they're a good series. And in this series I'm running now, I'm going through the first book, which is sort of the more recreational one. This is sort of recreational, kind of advanced high school level math. Anyway, so I've been talking about number systems. Today I'm going to talk about binary, also known as base 2. So, what is base 2? Well, I made a few videos about a year ago about arithmetic and different bases. I think I also made one on binary system. So the system we use to count today is what's called the decimal number system, and the reason it's called decimal stands for base 10, and it involves 10 different symbols for every digit, the numbers 0 through 9. And similarly, you can have any base you want, and the smallest possible base is base 2, and this one only has 2 symbols, namely 0 and 1. And it's a very commonly used system because it's used by computers. I mean, every number that's represented inside a computer is a binary number, and the reason for that is because the zeros represent no current flowing through a particular element of the circuit. 1 represents a current. So either current's on or off, 0 or 1. So that's why binary is kind of a natural number system to work with for computers. And it's useful to know how to compute between binary and decimal. And just to give you an example here, the example I show here is the number, I guess to give you a binary number. And it's actually easier to convert from binary to decimal. Let's do that first. So the way you convert from binary to decimal, you have this number here, 101101. That's a binary number. All the digits are 0 and 1. And we want to know how to convert that to decimal. Well, it's really not that hard. I mean, just like for decimal, the value of each it's a place valued system. The bit on the digit binary digits are called bits, by the way. So the bit on the right is a 0, so we don't have to worry about. Or no, wait, it's a 1 actually. So that's the ones place. So we had 1, and then the next bit is 0, so we don't worry about that one. The third bit from the right is 1 again, and that represents 2 squares. So just like the rightmost bit is the ones column, the next one over to the left is the twos column, the one over to the left of that is the fours column. So the one to the left of the rightmost one represents 4. So far we have 4 plus 1, which is 5. But then there's another 1 to the left of that one. That's the eights column. So we have to add 8. That'll give you 13. And then the next one's 0, so we don't worry about that. That's the 16 column. We don't add any 16. But then the last one's a 32 column, and that's a 1 again. So we add 32 to the final result. That gives us 13 plus 32, or 45. So that's how you would convert from binary to decimal. Pretty straightforward. And, computers themselves don't have to worry about decimal unless they, output the answer. I guess you have to, program this into the output because humans use decimal and we want the computer to convert our final result to decimal when we're done. And here's another little bit more complicated example. Here's a bigger binary number, 1101010001. And I'm not going to go through this example in detail, but it's the same idea. And, if you want, you can sort of shortcut it. You can just keep track of all the places, which is what I've done here. And since this number has what is it, 10 bits, the leftmost bit is 2 to the ninth, so we add 2 to the ninth, and the one next to that the 2 to the 8th column, so we had 2 to the 8th. There's no 2 to the 7th, but there is a 2 to the 6th. And there's no 2 to the 5th, but there is 2 to the 4th. And there's no 2 cubed, 2 squared, or 2 to the 1st, but the last one's 2 to the 0 or 1. So we just add up all those powers of 2, and when you do that, you get 849. So you can do it for any number you want. It just gets more complicated the bigger the numbers are. But then we might want to go the other way around as well, and that's a little trickier. So if we want to convert from decimal to binary, there's actually two ways to do that. There's two methods for doing that. There's what's called the top-down method and the bottom-up method. So I'm going to go over both of these methods. So the top-down. So let's just give an example here. Well, actually, I'm going to talk about the algorithm first. So this is a computer algorithm for doing a top-down. Basically, the idea is you start with a number. It'll probably be easier if I do an example, but yeah, maybe I shouldn't go over this algorithm because it probably won't make much sense to you unless I show you an example. So let me show you an example here. Let's convert the number 345 to binary. And what do? Well, you look for the biggest. This is also known as a greedy algorithm. We look for the biggest power of 2 that's less than or equal to the number we started with. In this case, 345. That happens to be 256, or 2 to the 8th power. So we write down a 1, and then we note that that's really in the 9th place, or the 8th place to the left of the rightmost digit. And then we keep going. We subtract 256 from what we started with, 345. If you do that, you get 89. And this time the biggest power of 89 that's less than or equal to that is 64, 2 to the 6th. And since we started with 2 to the 8th, that means that we have a 0 for the 2 to the 7th place, but then we put a 1 for the 2 to the 6th place, and that gives you 101, but then there's still 6 bits remaining that we have to fill in. And then when you subtract 64 from 89, you get 25. 25, the biggest power of 2 that's less than or equal to 25 is 16. That's 2 to the 4th. So that's going to give you a 1 and then 2 to the 4th column. So far we have 10101. And then when we subtract 16 from 25, we get 9. 9, the smallest power of 2 that's less than or equal to 9 is 8. 2 cubed, and we already did 16, so that goes right next to it. So now we're going to have 101011, and then when you subtract 8 from 9, you get 1. That's just the last binary digit, the last bit, and there's no 2's or 4's, so we write 001. So the final result is going to be 10101001. That's the binary, or 11001. That's the binary representation of 345. So I think you get the idea. And you can do this for any number you start with. And actually, there's another algorithm, which I think is actually a little bit better. It's called the bottom-up algorithm. And maybe it's not as intuitively obvious why it works, but it does work. So the idea with the bottom-up algorithm, this time, in the top-down, we were writing down the bits going from left to right. In the bottom-up algorithm, we write the bits going from right to left. And it's actually a pretty easy algorithm. It has fewer steps. Notice that the top-down algorithm had, I think, 8 steps. The bottom-up algorithm only has 4 steps. And the first thing you do is you check the parity of the number you started with. In other words, whether it's even or odd. And if it's even, the rightmost bit is 0, and if it's odd, the rightmost bit is 1. And I think that actually kind of makes sense to you. Every even number in its binary representation ends in 0 because there's no ones. If it was a 1, it would the rightmost bit would be 1, but that would mean the number is odd. And if the rightmost bit is 0, that means you have to go to the 2's column or higher in order to see your first 1. So that means that the rightmost bit is 0. So you check the rightmost bit. And you check whether the number's even or odd. And like I said, if it's even, you write a 0. If it's odd, you write a 1. So that's the first step. And then once you've done that, you divide your number by 2. And you might have to subtract 1 first. It turns out that if the number was odd that you started with, you have to subtract 1 and then divide by 2. Another way to say that is you can divide by 2 but round to the nearest integer below. the floor. So you take the floor of n over 2, and you make that your new n. And then you just do as you did before. So you look at the new number, you see if it's even or odd, and if it's odd, you write a 1. If it's even, you write a 0. Keep going like this until you're left with 0. And then when you're done, you'll have the binary representation of the number you start with. Kind of a neat algorithm. I think it's easier than the top down. And I think most computer algorithms that convert decimal to binary do it this way because I think it is more efficient. Anyway, I'm going to do the same example. I'm going to convert 345 to binary again using this time the bottom up algorithm. So what do? We check the parity. 345 is odd. That means your rightmost bit is 1. And then you take the floor of 345 over 2, which is 172. That's even. That means that the next bit to the left is a 0, and then you keep going. 172 divided by 2 is 86. Again, that's even. So you write another 0 in the third, in the fours column. And then you do this again. 86 divided by 2 is 43. And 43 is odd, so that means you're going to write a 1. And then you take the floor of 43 over 2, which is 21. Again, that's odd, so you write another 1, and then you take the floor of 21 over 2, which is 10, and that's even, so you write a 0, and then you take the floor of 10 over 2, or 10 over 2 if you like, and that's 5, and that's odd, so you write a 1, and then you take the floor of 5 over 2, which is 2, that's even, so you write a 0, then you take the floor of 2 over 2, which is 1, and you write a 1 for the last one. And then you're done because the floor of 1 over 2 is 0. So that's how that works. And anyway, I think that concludes my video for today on binary representations, numbers, or base 2 in other words. And thank you for watching. Long live math, and I'll see you guys next time. Bye.